ever since the onset of computing, humans have been trying to define and then simulate human intelligence. And by virtue of doing so, we've come up with this war chest of algorithms and techniques that mimic various facets of human intelligence, and sometimes biological and natural intelligence. And this war chest of algorithms is effectively called AI. Typically, you pose the problem to the algorithm, and the algorithm comes up with a solution or a model for the world. And so we don't have a very exact definition, but that also is the case for intelligence itself. I think it's going to percolate through various different industries, and its applications, especially in sensing the world and modeling the world, is going to get more and more pervasive. In certain autonomous situations where the frequency of decision making is high, AI can be used, and I think increasingly we'll see applications of that. But you know, it's difficult to come up with an application area where AI does not have a role to play, either in augmenting humans or in even replacing them. So I think as our techniques become more and more powerful, we're able to use them in more and more places. And there's a lot of interest as well, and pull from different industries and different domains, and that will also help spread the use of AI techniques. For me, the story was, I like to figure things out. So after I felt like I figured out how computers work, then I got interested in figuring out how the brain works. And once I felt like I kind of had the essentials of that figured out, then I was interested in how nature can produce something as complex and powerful as the human brain or life itself. And inevitably, you look at things like evolutionary computation as the underlying mechanism for improving and adapting, and that's how I ended up in that field. Evolution can be used in black box optimization, where you don't really have to have a very good model or definition for what the solution looks like. And you might not have a very good feel for what the search space of possible solutions looks like either. And so evolution does a very efficient job of finding acceptable solutions in very large search spaces. It also allows for optimization against multiple objectives. You're not just solving for one objective. You can actually have a combination of objectives. And by virtue of doing so, it gives us a sense of what is possible. It gives you a spectrum of good solutions. So for all of those reasons, evolution is a great method for tackling complex problems. In today's world, not only do we have evolutionary algorithms that scale very well, but we also now have the means and compute capacity to run them at very large scale. So we can tackle problems that are quite complex in this manner, and problems that are difficult for us to design solutions for. So for that reason, we initially were quite interested in this approach for trading in the stock market, and as we came up with good solutions there, we realized that the approach is generalizable to other complex problems as well. So we looked at other areas, namely digital marketing. We've also, in research, we've applied it to a number of other areas, such as cyber agriculture and healthcare and such. Digital marketing includes a decision loop that is all contained and automated, and there's a lot of data that can be collected that can help direct that decision making. From the moment where you engage a user until you take them through that journey to whatever you're trying to convert them on, you can, that journey is digitized and can be measured. For example, at the simplest level, if the end user gets to the button you want them to click, and whether or not they click on that, that's a measure that you have. And you're talking about large audiences, a population of users following that journey, whether or not they actually react to an ad or whether or not they end up buying something in an e-commerce site. And so you can capture that variability in an adaptive manner. In other words, as the world changes and as the preferences of users change, if you have an AI system that can adapt to that, then you can maximize the conversions in a digital marketing journey. So for a number of reasons, it is interesting. As opposed to, for example, you look at healthcare and how in biology things are not as deterministic. It's difficult to try different things out. There's implications to that. You're dealing with human livelihood. You might not have as large a population to draw from to learn what your search space of solutions look like. So just contrasting that to other domains, digital marketing seemed like a very natural next area for us to focus on. And if you think of where we started, which is in trading, it's very similar. Again, in trading, you kind of have many examples, and there's a lot of data and historical data that's collected, and the fitness, if you like, is built in. If you do well, you get, you make money. If not, you don't, and it's kind of multi-objective. You want to do that consistently, so that consistency is another objective that you have in there. But the entire decision loop is contained in the problem, and it can be measured, and you can try things out. And it calls for an adaptive solution, because the world in trading or in digital marketing 6 months ago or a year ago is probably a very different world than where it is today. So you want to be able to keep up with the underlying models and laws governing how people react to digital marketing or how markets operate. The one that was the most surprising was when we applied evolution in a black box optimization setting for cyber agriculture, where the problem was coming up with recipes for growing basil in a completely controlled environment. And the system ended up discovering things that we already knew, which is the larger the plant, the less tasty, and you can measure taste through measuring volatiles in the leaf. But also, it ended up discovering something we didn't know, which is that basil does not really need to sleep, and if you shine light on it 24/7, it kind of thrives. So that was something that was unexpected, and the evolutionary system discovered that. I mean, deep learning is deep learning, evolutionary computation is evolutionary computation, but in its power to adapt and its power to scale, it's quite unique. And so, and the fact that it's a generalized solution, so you can actually apply it to many, many different problem domains. So it has characteristics that are analogous to deep learning. I don't think they're exclusive, and often actually in our application areas we use them together. For example, we evolve deep learning architectures to come up with better deep learning solutions. But I think in that statement, what is trying to be conveyed is the fact that the same level of attention that is afforded to deep learning, I think, is justified to be paid to evolutionary computation too, both being techniques that were invented 30, 40 years ago and showed promise in the lab, but were not scaled, did not scale that well, and today they do scale. So in that regard, yeah, I do believe that the time has come for the world to pay attention to evolutionary computation. Yeah, we do need to make evolutionary computation more accessible and educate people as to how to use it. Put some of our platforms out in the cloud and show how easily you can actually use them to tackle a spectrum of different problems. So I think we've seen the power of evolutionary computation. I think there's a next step there, which is to kind of get it in the hands of developers and data scientists and show areas where it does quite well, and allow them to use it. So that's one area. Evolutionary computation itself has many different incarnations, many different facets. There's a lot of research that's going on. It's still a fraction of the research that's going on in data science, so we do need to get more funding into research of evolutionary computation. The talent, if you think there's a shortage of talent around deep learning in the world, there's a very small fraction of that available talent for evolutionary computation. So that's more on the practical side. On the science side of things, there are still problems in, for example, genetic programming and generalization of evolutionary computation, baselines, coming up with good benchmarks. The field needs to evolve and mature, and hopefully with the attention that it's starting to receive increasingly, that we're going to get there. Yeah, evolution can be deceptively simple, but there are a lot of hyperparameters, just like deep learning, that you can, if you don't set properly, you might not get the results that you're looking for. At its essence, it's very simple to describe. Same thing actually for deep learning and neural networks. Their essence is simple to describe. But the science and technology has come a very long way. And so the state of the art and best practices do take a while. So the first thing I would ask is to be patient with it. And hopefully as they realize the power of it, it will give them the patience to learn and master it to the point where they can actually get the benefit. To democratize AI, we have to make it simple to use. It's starting to happen a little bit in certain areas. If you want to do image recognition or object detection or speech recognition and so forth, there are libraries now, and there's off-the-shelf models that you can use. I think in areas such as natural language and conversational systems, increasingly there's available resources that, again, off the shelf you can use and plug into your system. You can create a chatbot pretty quickly. I think that there will always be a need for some level of data science that goes into tackling more complex problems. In order to pull from the various different techniques. I mean, we talked about evolutionary computation, but there are techniques that are quite relevant that are not as popular or don't have as sexy a name like deep learning, but things like, you know, random forests and Bayesian methods and so forth that are very well suited for certain problem areas. So, you know, that's where a data scientist comes in to actually look at that available war chest and pick the ones that apply for a certain problem area. So I think that just as 30 years ago, you know, people talked about computerizing different enterprises, and there was a computer department, and people came in and looked at processes and started computerizing things. Today, that's kind of laughable. You know, we are all computer scientists and we are all computer users by those standards, and everything is more or less computerized, and at least our fields. I think the same is gradually going to happen with AI, and we won't even call it AI anymore at that point. We will know what kind of AI to use for what kind of problem, and we'll just apply it. Should be as easy as that.